So hello everyone. So good afternoon to all. So let us continue our lecture number 7. And so let me just recall that in the previous lecture we were trying to give an equivalence condition when a Gaussian when if you take a prime integer, when it will be a Gaussian prime or a Gauss prime inside the ring of Gaussian integer. Yeah, and in that, so we have given 4 equivalence conditions, and if I so let me just try to yeah, just show that. So this is the thing that if you take a prime integer p, and if this prime integer is splits inside the ring of Gaussian integers, then of course it will be a sum of 2 squares. And now the third equivalence condition is that the congruence, this if you try to look the polynomial x square plus 1 inside z mod pz, so they will have a solution inside z mod pz. Yeah, and the fourth one is that actually it classifies arithmetically that what will be these prime integers, they will be congruent to 1 modulo 4, or p prime p is equal to 2. Yeah, and so in the previous lecture we have proven one if and only if 2, and then we also gave the proof of one if and only if 3 modulo certain lemma. Yeah, and so today we are going to prove that lemma, and then we will proceed further. Yeah, and so the lemma that we have used is that what does it says that if you take a prime integer p, yeah, then what does this lemma says? Actually, in a sense, what I should say that this is exactly the conditions that we need to prove one if and only if 3. And here see that p uh, in this one, p splits inside the Gaussian ring of Gaussian integers, and a contrapositive statement is p, if p doesn't split inside the ring of Gaussian integer, so it has to be a Gauss prime. And that is thanks to the theorem A that we have proven that if you take a prime integer, so either it will be a Gauss prime or it splits. Yeah, so if it doesn't splits, then this will be a Gauss prime. So it is exactly the contrapositive of this one. And the here the third condition is exactly the corresponding to that. Yeah, whatever we have in the theorem. And the second, actually the second here is actually, I should say, second equivalence is actually an intermediate step to prove one if and only if 3. Yeah, so the second step is automatic if one would like to prove 1 and 3 equivalence. So it actually, second step helps to come from Gaussian prime to the modulo p thing via this ring, which is a field. Yeah, okay, so let me just start with the proof of this lemma. So in order to prove this lemma, so let me just recall how we can algebraically look the ring of these Gaussian integers. And so we have a very natural substitution homomorphism that we know. So let me just recall. So probably you all know these things from the previous lectures. So let me just recall that what I can here recall that. So what we have, that if you look this polynomial ring with integer coefficients, so z of x, yeah, and z of x that we have to zi, yeah, so we have this thing, and this is the natural substitution homomorphism. If you would like to give a name, let's say phi, what you do, f of x, you just send to f of I. Yeah, and that is a ring homomorphism. And then if one would like to see the kernel of this ring homomorphism, then one can check that the kernel of this homomorphism is precise. Of course it is an onto ring homomorphism, because any element here, if you try to take for example a plus bi, so there will be a linear polynomial with integer coefficient a plus bx. Yeah, and of course if you have a polynomial with integer coefficients, then if you evaluate, then you do get you do get some element of this ring zi. Yeah, and so kernel, if you try to compute, so kernel of phi, and you can check that this will be exactly the ideal generated by the polynomial x square plus 1. And so therefore what one can say that so z, so this polynomial ring, if one goes modulo this x square plus 1, and I think this is the first isomorphism theorem that you have studied. This is isomorphic to this polynomial ring of Gaussian integer zi. Yeah, and now so what we can now do that, let's try to take a prime integer inside so zi. So p, if we take p belongs to z, and of course this z is all is a subset of this ring of Gaussian integers. And now we will look an ideal generated by this prime p inside zi. Yeah, and so let us denote this by say pzi, and this is exactly, for me the notation is the ideal generated by p inside this ring of Gaussian integer. Yeah, and then what one can do, one can again go to the quotient, so zi modulo this ideal generated by this p. Yeah, so this is a ring, so that we will give it as a name, say r dash. And so what we see that this r dash, this ring is obtained by if you try to identify zi by this polynomial ring zx modulo x square plus 1, then what we can see that this r dash is obtained. So r dash is obtained by introducing two relations in the polynomial ring with integer coefficients. And these two relations, if you try to see that, so zi one can think of zx modulo that thing. In this ring we are putting the condition that x square plus 1 should be 0. So that is the one thing, that x square plus 1 is equal to 0, and this prime p, whatever we have taken, is equal to 0. Yeah, and if you put these two relations in polynomial ring zx, and then one can see that this ring r dash is obtained by putting these two relations. And what I would like to say that in fact I think this third isomorphism theorem you also have studied. In fact, one can prove that this actually doesn't matter that which of the relations you first use. For example, if you use first this relation and this, then this relation, or other way around, then you do get the same ring r dash. Yeah, so using this, what we have actually done, that we have, by introducing these two relations, we have seen that that x square plus 1 ideal generated by x square plus 1 and p can be shown to be isomorphic to this zi modulo this principal ideal generated by p inside the ring of Gaussian integers. Yeah, so this is the thing that one can verify by the third isomorphism theorem, and this we are giving it as a name r dash in our previous lecture that I think have notation here. So so here I have notation r dash we have taken to be zi mod p. But here, so in this one, what I would like to comment here, that a priori it is not clear that this will be a field, and in fact, actually this lemma says that this always may not be a field. Yeah, this lemma actually says that this r dash may not be always a field. It depends actually on the prime p, prime integer p. Yeah, and so it will be a field precisely when the prime integer is a Gaussian prime. Yeah, so and that's the exactly thing that we would like to prove. And so that so a priori it is an integral domain, that much we can say from here. But it will be a field precisely when that p should be a Gauss prime, and that's the thing we would like to prove. Yeah, so let us start with the proof of uh, so let us start with the proof of lemma. So proof of lemma. Yeah, so so by the way, my screen is visible because I got a notification that participants can see your screen now.
Sir, it is visible.
Yeah, it was visible from the very beginning or from now onwards?
From the very beginning.
Okay, good, because just now I got a notification. Okay, no problem, good. So by the way, any questions or comments?
No, sir.
Yes, sir.
Okay, good. So let us try to first prove one if and only if two of this lemma. So again, I have to go again and again. So, and it is starting with the very beginning. So this is the exactly lemma that we would like to prove this one. So this is the lemma that we would like to here prove. And so one says that suppose P is a Gauss prime, then we need to prove that the quotient ring actually is a field. Yeah. And that's obvious because we know that Zi is a Euclidean domain. Yeah. So is a principal ideal domain. Yeah. So let I think that is obvious. So one implies two. That now R dash, if you try to write it quotient Zi by P, ideal generated by P, that this is a field. This is a field just because one can write that P is prime in this Zi, and we know that, and Zi is a PID. Zi is a PID, so every prime element will be irreducible and prime elements are same, and we have proven that in a PID maximal ideals are precisely generated by the irreducible element. Yeah, so this will be a maximal ideal. Yeah, Jedi is a PID. This implies that ideal generated by P is maximal. Yeah, maximal, and hence let me this may confuse, and so let me just write down that. So let me just write down this thus ideal generated by this P is a maximal ideal, and therefore the ring, this is a field. Yeah, and the two implies one is again obvious, because again one need to use the property that uh, Jedi is a PID, because this is a field, that means this is a maximal ideal, and then since being a PID, this will be an irreducible element, and in a PID irreducible and primes are same, so P is a prime inside Zi, so is a Gauss prime. Yeah, so now let us try to prove one if and only if three. Yeah, and in order to prove one if and only if three, what we are going to assume, in fact, that we are going to prove that two implies, we will assume that this is a field. So we will assume two, and then we will prove three. Yeah, and conversely also, if three holds, then we need to prove maybe two, three implies two, or three implies one. Yeah. Okay, so let us try to prove this thing. And so in order to prove what we need to see that what we need to prove that, so let me just see this lemma. And in this lemma, what is the second statement? That this ring is a field, this R dash is a field, then we need to show that x square plus 1 is an irreducible polynomial in the polynomial ring with a finite field Z mod PZ. Yeah. And now, so the role of these things that we have studied here will play a role. And as I told that it doesn't matter which of the relations we use first in order to get R dash here. And so here, so for our, in order to prove our theorem, or in order to prove our lemma, we will first use the prime that P is equal to 0 relation, and then we will try to use that x square plus 1 is equal to 0 relation in this polynomial ring with integer coefficients. Yeah, so let's suppose these two holes. Yeah, and then we need to prove that 3 is true. And so in order to do, we have this substitution homomorphism zx to z mod pz. Yeah, x, and just f goes to f bar is the reduction mod p ring homomorphism. And we know that this is a surjective map. Yeah, this map is surjective, so let's say it is psi map. so note that psi is a surjective map. Yeah, because if you take any element here, so they will be the coefficients coming from z mod pz, and of course if you just simply take those as an integer, so you do get a polynomial with integer coefficient. Yeah. So therefore it is surjective, and therefore first isomorphism theorem says that zx uh, modulo the kernel will be isomorphic to z mod p z of x. Yeah. And if you try to see the what will be the kernel in this case, and kernel is precisely all those polynomials with integer coefficient, if we reduce it modulo p should be identically 0, and that means each of the coefficients is divisible by p, so that should be a multiple of p. Yeah, so p times zx. Yes. And therefore what we see that this is the first relation that we have used. Now we can use the second relation, which is x square plus 1. X square plus 1, that thing is equal to 0. And so if we try to use that relation, so what we can see that z mod pz of x, and if we use the relation x square plus 1 equal to 0, that means we need to go modulo the ideal generated by x square plus 1. And one can in fact prove that if one tries to use third isomorphism theorem that you have studied, then one can prove that this thing is precisely isomorphic to the ring R dash. So this will be isomorphic to this thing R dash. Yeah. And that R dash we if we try to see the notation, so this is exactly zi by zi by p. Yeah, maximum means ideal generated by this prime integer p. Yeah. And now so what we have assumed that 2, since 2 is true, so this implies that now since R dash is a field, since R dash is a field, yeah, this is by 2. This implies that this ideal generated by x square plus 1 will be a maximal ideal. So this x square plus 1 is a maximal ideal. And now I think the proof is again a routine argument that we have given just above. Uh, that if it is a maximal ideal inside the PID, z mod pz of x is a PID, because z mod pz is a field, so fx is a PID. And so therefore in a PID maximal ideals will be actually corresponding to the irreducible element. Yeah. And since z mod pz of x, this polynomial ring, is a PID, so this implies that x square plus 1 as an element, x square plus 1 is an irreducible element. X square plus 1 belongs to z mod pz of x is an irreducible element. Yeah, irreducible elements is, since it is a polynomial, so is a polynomial, irreducible polynomial. Yeah. And now I think converse is also obvious, that one can verify that if you have an irreducible element inside this thing, so the ideal generated by this will be a maximal ideal. And so if you look at this quotient, yeah, so this will be isomorphic to R dash, and therefore R dash is a field. Yeah, because this quotient by if you quotient by a maximal ideal, so that will be a field. Yeah, so therefore converse is also obvious. Yeah. Yes. And so therefore this actually proves the lemma, and actually in a sense it proves that one if and only if 3 in that thing is true. Yeah. So by the way, any questions or doubts? So from here actually, yeah, if I can remember one thing that in the previous lecture, so we have a question whether so zi by p uh, is isomorphic to z mod pz of I, whether it is a field. So as one thing is clear that this a priori always may not be a field, because it depends on prime p here in the Gaussian integer. Yeah, and it is so this is precisely a field when it is a Gauss prime. So if the ordinary integer prime is splits, so this cannot be a field because otherwise it violates this equivalence. Yeah, so that one thing that I would like to say. And so this is about this thing that one if and only if three. And now our aim is to prove that if we try to see this equivalence here, so this one, yes. Now we need to prove this fourth equivalence with any one of them. And this fourth equivalence, actually, we would like to prove that 3 implies 4 and 4 implies 3. Yeah. And then if you prove, then it completes this equivalence of this theorem. And the fourth one actually is easy in a sense to compute what are the primes which are not Gauss primes. And they are precisely primes which, if you divide by 4, leaves the remainder 1. R prime p is equal to 2. Yeah. Okay, so let us try to move. So our aim is to prove. So now let me just write down that aim is to prove this 3 if and only if 4. Yeah. And so what does 3 says that the polynomial x square plus 1 is reducible inside this thing, reducible in z mod pzx. Yeah. And so what we need to show that is equivalent to prime p is equal to 2 or all primes p congruent to 1 mod 4. Yeah. Now let us try to see the thing. So that means, so what does 3 says that x square is congruent to minus 1 mod p as an integer solution. As an integer solution. Yeah. And so therefore, if you try to look for p is equal to 2, what will be the p is equal to 2? Yeah. And so what we have that if we take p is equal to 2, then of course this has a solution. So x square plus 1 is equal to 0 modulo p, and this is modulo 2 here, and this is just because this if you take x is equal to 1, that do the job. Yeah. So therefore what we would like to say that if p is equal to 2, then this has a solution, precisely x is equal to 1 will do the job. And so therefore what we see that 4 implies 3. 4 implies 3 for p is equal to 2. And now we need to prove this thing for odd primes. Yeah. And for odd primes, we need to check whether such a thing holds or not. And in order to see this, actually, we need to again prove a lemma. And so what does this lemma actually says? So for odd primes, so we need to look for odd primes p prime p, and so this is the lemma actually helps us to prove this equivalence. And what does this says that if you take p an odd prime, and then here is the first statement. What does it says that the if you try to look the congruence x square which is minus 1 mod p, this this has integer solution, has integer solution integer solution if and only if uh, 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 so let's say this has integer solution a if and only if a bar uh, is an element of order 4. So a order of a is 4 if you would like to see inside the field z mod pz. So let me just write it is in the sort that if and only if order of a bar is equal to 4 in the field say z mod pz or fp. Yeah. So what does it says that this congruence has a integer solution, then the order of that particular element will be 4 in Z mod PZ, if and only if. And the second statement is about this, if you try to look this, so this is Z mod PZ is a field, and so therefore that means the, if you look the multiplicative group, so that will be again a that will be a group we know. And if you also know from group theory, that is a cyclic group, yeah. And so of course, if you try to look the order of this, if you try to look the order of this multiplicative group will be p minus 1, yes. And so p minus 1, and here the second condition actually says that if this multiplicative group has an element of order 4, if and only if it is 1, this prime p is 1 mod 4, so that Z mod pz star contains an element of order 4, element of order 4, if and only if this prime p is 1 mod 4. Yeah, so these two things. And so therefore what this actually says, that if you assume 3, and 3 says that x square congruent to 1 mod p has an integer solution, and 4 we need to prove that p is 1 mod 4, yeah. So from this lemma, what it will be clear that we have given this statement, this will imply that order of an element, order of that element, if you reduce modulo p, will have order 4. And the second part says that this that element has order 4, that means the prime is congruent to 1 mod 4, yeah. And conversely also, if you assume 4, that means p is congruent to 1 mod 4, then this part b says that this multiplicative group contains an element of order 4. And then if you use part a, reverse implication will says that part 3 of the theorem follows, yeah. So this actually will prove the result for odd primes and even primes that we have already sketched. So therefore what we have seen that this theorem follows, yeah. And so let us quickly see the proof of this lemma, and then we will proceed further. So let us try to see the part A. And part A, what does it says that x square this polynomial, actually x square plus 1 has a solution in Z mod pz, yeah. And so therefore what we would like to see that if you try to see what are the order 2 element inside Z mod pz, so order 2, that means with respect to the multiplicative group I am talking order 2. And so order 2 elements, if you try to look, that means all those elements for which this x square minus 1 is equal to 0. And we know this is a field, so it can have at most 2 solutions inside this. And we know that plus minus 1 are actually the elements, and minus 1 is precisely having order 2. So there can be exactly one element whose order is 2 inside this Z mod pz, yeah. And so what we would like to prove here, that if we have given that x square is congruent to minus 1 mod p, then of course that thing then, so what I would like to prove first, that this has a solution. So aim is to prove that there exists an element of order 4. That's obvious, just because so suppose a bar belongs to Z mod pz you have, such that a square is minus 1 mod p, that means what, a bar square is minus 1. And so this will implies that order of a will be 4, because a bar to the power 4 will be exactly equal to 1, and no lesser power will give 1, that one can check. And so therefore that is order of this element a is 4, Yeah, and conversely, what does it says that if you have an element of order 4 inside Z mod PZ, then actually we have a solution for this polynomial inside Z mod PZ. Yeah, and so therefore what we would like to conclude that conversely, so let me conversely suppose conversely if there exists an element a bar in Z mod PZ such that order of a bar is equal to 4, and so therefore if you would like to see what will be a bar square has to be equal to -1. Yeah, because what we know that there is exactly one element of order 2 inside Z mod PZ. Yeah, and that's precisely this thing -1. Yeah, which has order 2. And what we see that therefore a bar, if you take the square of this element which has order 4, has to be equal to -1, so that a to the power 4 will give 1. And so therefore here a square is congruent to -1 mod p as a solution. Yeah, and so therefore this proves the first part. And so by the way, any doubts or comments so far? So
No, sir.
this is just a routine things that we do in maybe group theory, or in fact this proof is exactly the arguments coming from group theory, nothing else. Yeah, second part actually is using hardcore group theory, part B. That's one we would like to prove now. So let us come to the part B. So what this part B says, that if you have this thing, if you have the multiplicative group, if it contains an element of order 4, then we need to prove that this prime is congruent to 1 mod 4. Yeah, and so therefore what we need to, so one part is obvious from the very group theory, and that's this is I think exactly say Lagrange's theorem or what. So if you have an element of order 4, then order divides the cardinality of the means order of the group. Order of an element divides order of the group. Yeah, so direct part, this part is obvious. This is obvious by Lagrange's theorem. Yeah, the Lagrange's theorem, because this part says that there exists an element of order 4, and Lagrange's theorem says that order of an element divide order of the group, and order of group is precisely p minus 1. So therefore 4 divides p minus 1, which is exactly equal to this thing. Yeah, so this thing is obvious. Now we need to prove the converse part. That means suppose p is congruent to 1 mod 4, that means 4 divides p minus 1. And then what we need to prove the existence of an element of order 4. And again, it is a group theory that we are going to do. And since we know something divisibility about the order of the group, that means 2 square divides p minus 1, which is the order of the group Z mod pz star. So p minus 1 is the order of Z mod pz star. Yeah, here. And so we can talk about so-called the CELO p subgroups, and here we can talk of CELO 2 subgroup, and let's say H be the CELO 2 subgroup of so let's say CELO 2 subgroup of Z mod pz star. Yeah, because 2 square divides, so you look the highest power which highest power of 2 which divides p minus 1. Yeah, and that we are calling as a CELO 2 subgroup of Z mod pz star. Yeah, and what we have given that since 4 divides p minus 1, so therefore order of this subgroup H is at least 4. Yeah, and so so it may be maybe more power of 2 divides, and CLO2 subgroup is the maximal such order. But since we know this much, we can say that order of H is at least 4. And so therefore in H we will have a element A belongs to H such that A is not equal to plus minus 1. Yeah, because H contains at least 4 elements. And of course you can see that this element A that will not have order 2 or 1. Yeah, because this is different from plus 1 and minus 1, and order 2 element we know is precisely minus 1 is only one element which has order 2 in this thing. Yeah, and so therefore this has order neither 1 neither 2. And in a CLO 2 in a CLO P group, in a CLO P subgroup, or CLO, for example here CLO 2 subgroup, order of any element will be a power of 2. Yeah, so that's exactly we can write that. But uh, so note that, so here let me write down the note that order of A bar cannot be equal to 1 or 2. But since H is a CLO, H is a 2 group, H is a 2 group, so order of A bar will be a power of 2. Yeah, and hence what we know by these results from the P group results, that order of hence order of A bar is a power of 2, is a power of 2. Yeah, so therefore order of A will be power of 2, so it may be maybe say 2 to the power 4 or 2 cube or something like that. Yeah, so whatever order it will have, which cannot be 1 or 2, then we can make a suitable element from this order to make an element of order 4. Yeah, and that's the argument, that so some power of A, so some power of A give uh, will give uh, will give an element of order 4, an element of order 4. What does mean that, so it will not be 2, so it cannot be 3 because it has to be a power of 2. So if it is 4, if order is already 4, then we are done. If it is more than 4, it has to be 2 cube. But if you have 2 cube, then we by taking a suitable power of A, we can find that that suitable power of A will have order 4. Yeah, and that's the argument that that proves the existence of an element of order 4 if 4 divides P minus 1. Yeah, and so therefore this in a sense completes the proof of the theorem in the previous lecture that we have started here. And so therefore we precisely know what are the Gaussian in what are the prime integers which are Gaussian primes, and what are if they are not Gaussian primes, they splits completely, then they will have precisely 2 factors. And so this gives actually the complete picture of integer primes which sits inside the ring of Gaussian integer as a prime element. Yeah, so okay, so far so good. So by the way, any questions or doubts, then we can proceed further.
No, sir.
Okay. Okay, so we are now going to discuss so-called this algebraic integers, and I think in the very maybe first or second lecture of this course, you might have been given the definition of what do you mean by algebraic numbers. So yeah, and also maybe algebraic integers. Does it has been recall means this has been defined, the algebraic numbers and algebraic integers?
Yeah, they are defined. I'm just looking students will say or not. It is defined. Sorry.
Okay, okay. So can some of you recall me what is the definition of algebraic numbers and algebraic integers?
Complex.
So let's say alpha belongs to C, is said to be an algebraic number. So algebraic, let me write in short, if now you please say.
It satisfies a monic polynomial over Qx.
If satisfies a monic polynomial over Qx, then it will call as algebraic.
Number.
So why monicness is needed for Qx? So
It is not needed.
yes, yeah, because if fx belongs to Q of x, such that f of alpha is equal to 0. Yeah, and what is algebraic integer?
If it satisfies a monic polynomial over Zx.
Yes, is algebraic integer. Let's say if there exists polynomial f of x belongs to z of x, let's say f of x such that uh, uh, f of x is a monic, that means x to the power n plus what I would like to say plus an minus 1 x to the power n minus 1 and so on so forth a naught. Yeah, for with f of alpha is equal to 0. Yeah, so these are the two definitions that you have studied, and if you try to see that whatever we have discussed are in the previous lectures in this course on algebra, so you have seen that the results, general results that have been discussed actually does not play, actually is not very much related to these notions. Yeah, uh, but and actually the thing that I would like to say that although they in the general this results that we have seen, they may not have any direct use, and but in number theory they have a lot of applications and lot of results which actually is central to these notions, algebraic integers and all. And so the thing that we would like to just say that for example the notions that Euclidean domain, principal ideal domain, or unique factorization domain, whatever we have discussed, and in order to discuss those things, our role model that we were taking as the that properties is already valid inside ring of integers z. Yeah, and then by looking the arithmetics that we have inside the ring of integer, and these properties we would like to generalize for general integral domains. And at the very beginning, when these notions were trying to generalize, actually what people would like to say that whether these properties which is there inside the ring of integers actually is true for algebraic numbers or not, or for algebraic integers or not. Yeah, and that's what the place where this notion of algebraic numbers actually comes in this lecture, and we would like to discuss a bit of them. And so let me just say that in number theory, of course, they have many applications, and let me just sketch or give the motivations how these algebraic integers are actually have applications in number theory. And so usually one is always interested, for example, in number theory, is to find the integer solution of certain, say, equation. If you have given, for example, if you have given equation of, let's say, circle, so x is not circle, so let me just write down this one, x square plus say 5y square is equal to p. This is let's say equation of ellipse. Yeah, we have, and one is interested to find the integer points on this ellipse. Yeah, so to find the integer points on ellipse. Yeah, or if you would like to, let's say that if you would like to find the integer points on the circle of radius, let's say square root of p, x square plus y square is equal to p. And then what you can do, that you can factorize the left hand side, and you can write it as that x plus iy and x minus iy and is equal to p. And then what one can use the arithmetic inside the ring of Gaussian integer, arithmetic inside zi one can use, and one can actually discuss or analyze what are the integer points for this which lies on this circle. Yeah. And since Zi is a unique factorization domain, in fact is a Euclidean domain, so this factorization is unique and one can very well deal with the integer points. And here in this equation, so if one tries to analogously, if one tries to factor, then what one sees that this will factor like x, I think x plus I root 5. Yeah, I think yeah, x plus, let's say, square root of minus 5y, and then x minus square root of minus 5y is equal to p. And if you try to see that this, if you try to see integer solutions, then one need to study the ring, let's say z square root of minus 5. Yeah, and unfortunately what we saw here that this ring is not a UFD. So what we saw that this is not a UFD. Yeah, and so this factorization may not be unique, and one may not be able to precisely handle the integer points on this ellipse. Yeah, but here this factorization is unique, and one can deal with the properties which is inside this Zi, and one can find the integer solutions. Yeah. And so this is the thing that, and as we will see that this Zi or Z square root of minus 5 actually are the collection of certain algebraic integers. Yeah. So, and that's the place where in number theory one would like to, for example, so these are just, I am giving the simple instance where they do play a role, and to just to motivate to why actually one would like to study these algebraic integers. And the third example that I can give you why these algebraic integers are so important, for example, if you look the Fermat's equation of a special type, let's say x cube plus y cube is equal to z cube, and again here also one is interested for integer solutions, right? So for integer solutions, and then in order to study the integer solutions, one would like to write this thing as, if you write it as x cube as z cube minus y cube, and then one need to hit upon certain factorizations that we have studied, and therefore one would like to factor this right hand side. And if you factor this, so this will have three factors, so z minus y, and then z minus zeta y, and then so let me just write this as zeta, and then we have z minus zeta bar of y. Yeah, and here zeta is precisely the third root of cube root of unity. So here if you know the cube root of unity, which is complex, is precisely half of say minus 1 plus square root of minus 3. Yeah, and in the complex, the exponential, one can write it as e to the power 2 pi I by 3. So this is a cube root of unity, cube root of 1. Yeah, and we will see that this cube root of unity, so this zeta is an algebraic integer, and so in order to and so this factorization holds inside the ring that we are looking inside z of zeta. And so again this will form a ring of say certain algebraic integers, and again one need to study the properties. In order to handle these things, one need to study properties inside this z of zeta. And well, actually it is the, I think it is Euler who proved that this equation does not have any non-trivial solution, but the proof is not straight, not so obvious, and we will not go into the proofs of these things, but here it has been proven that it has no non-trivial integer solution. and the proof that has been given, in fact, for certain type of prime powers also, this Fermat's equation has been dealt with this by studying the ring of algebraic integer associated to those pth root of unity. No non-trivial integer solutions. And so non-trivial here mean that so trivial solutions are just if you try to take one of x or y or z to be 0 and other two as 1, then they are so-called trivial solutions. And it has been proven by Euler that it has no non-trivial integer solution, and but the proof is not so obvious and not so I should say not so straightforward, and we are not going into those things. So this is the just I would like to say that why these algebraic numbers and algebraic integers are actually important in number theory. And so let us now proceed further about these algebraic numbers and these algebraic integers. We will discuss a bit. And so as here we have seen that so if you have alpha algebraic number, so there exists a polynomial, say fx, yeah, let's say a0 plus a1x and so on so forth plus an x to the power n belongs to q of x, such that f of alpha is equal to 0. And now so these ai's are, of course, ai's are rational numbers, so they have certain denominators, and so one can clear the denominator of this polynomial to make this polynomial with integer integers. Yeah, so what we see that that we can make fx inside z of x such that f of alpha is still 0. Yeah, because if you just multiply the LCM of the denominators of these ai's to f of x, and then you can see that if alpha is a root of f of x, then if you multiply an integer to this f, will also have alpha as a root. Yeah, so we can make this polynomial with integer coefficients. Yeah, and what the definition differs from algebraic numbers to algebraic integers is that one need to normalize this leading coefficient. Yeah, so algebraic numbers definition, one can again say that if there exists a polynomial with integer coefficient for which f of alpha is 0, but algebraic integers require the condition that f of this f should be monic, and it should be inside z of x. Yeah, such that f of alpha is equal to 0. Yeah, alpha is algebraic integer. Yeah, so this is the thing that I would like to say. And now let us try to see certain algebra behind these numbers and what is going on. So if you try it, so we have a natural homomorphism which we call as the substitution homomorphism from q of x to c. And what one can do, just send x to alpha, and where alpha, of course, I am taking to be algebraic number here. And if you just send this indeterminate x to alpha and extend this map as a ring homomorphism, yeah, and extend this map as a ring homomorphism, yeah, then this is precisely, you have seen, is precisely the substitution homomorphism that f of x goes to f of alpha. Yeah, and so if we try to see what will be the kernel of this homomorphism, let's say it is phi. So kernel of phi is precisely all those elements fx belongs to q of x, such that f of alpha is equal to 0. Yeah, of course it is an ideal that we know, and since q of x is a PID, so therefore this kernel of phi will be generated by a single element. Yeah, and that single element that will generate is actually what we would like to say here. Also here what I would like to say, so that what will be this kernel of phi. So kernel of phi will be generated by, let's say, single element f1x. Yeah, now the question is, what is f1x? Can anyone say what will be this f1x? What will be this f1x? Any one of you? Means I mean to say that whether it will be an irreducible element or it is this f itself, for which f of alpha is 0. This f.
Irreducible.
Why? Why f1 should be irreducible? Sorry, I'm not able to hear. Why this f1 will be irreducible?
This will be the minimal polynomial.
Of course, yeah, least degree polynomial. Yes. Yeah, as you might have seen, even if you try to see the proof of that Q of x is a principal ideal domain, in order to prove that any ideal is a principal, what you try to prove, that you look at the minimal degree polynomial in that ideal, and then you say that this minimal degree polynomial will generate this one. And in fact, using those arguments, division algorithms and all, in fact, one can prove that this element will be irreducible. Yeah, let's say f1x is irreducible uh, in Q of x. Yeah, and here this is the thing, and of course so this will be irreducible in Q of x. And what I would like to say, that this alpha is also a root of a polynomial with integer coefficients, right? So therefore so what I would like to say, that if I restrict this substitute this phi on z of x, so if I restrict this phi on z of x to C, right? And of course, algebra, this alpha is algebraic number here. Then, so again, so f goes to again f of alpha, f of x goes to f of alpha. Then kernel, what will be the kernel here? Kernel of phi will be again, kernel of phi will be what here? So there we have used the fact that this is a what I would like to say, that this is a principal ideal domain. Then one can write like generated by a single element. But here we don't know. We know that ZX is not a PID. Yeah. Then how? What will be the kernel of phi? Phi restricted on say Z of x. Means what I would like to say here, that whether kernel of phi will be a principal ideal or not, first of all. If yes, then what will be the generator? Yeah, and that makes very much sense to ask, because it is not obvious at all in Z of x, though it was obvious here that will be a principal ideal because QX is a PID. So what is your guess? Yeah. So anyone of you, do you have any guess that will the kernel will be a principal is a principal ideal or not?
Yeah, I guess it is principal ideal.
Okay, so can you guess the element? Means what will be the generator then?
For f1x, there exists a polynomial in zx such that f1x equal to c into f0x and curve phi is equal to generated by f0x.
So let me just give a hint that, of course, one thing one can say that if means if alpha is a solution for integer polynomial, then alpha will also be a solution for a primitive polynomial. Yeah, because whatever GCD you have with this integer polynomial, you take that GCD out, then you can again see that alpha is also a root of that thing. Yeah. So that so if alpha is a root of an integer polynomial, that implies that alpha is a root of primitive polynomial. Yeah. And now since we are very much, and also what we are going to say that and you also know that uh, uh, if there is a polynomial for which f of x is equal to 0 in z of x, yeah, and we have proven that zx has a unique factorization domain. Therefore there will be if we write the factorization of this, yeah, say f1 of x and so on, say fk of x. And so if f alpha is 0, this implies that f1 fi of alpha will be 0 for some fi where fi is irreducible, yeah, and primitive, because they are integer polynomials. If alpha is a root, so is primitive. Yeah, means primitive polynomial will also have alpha as a root. Yeah, so therefore you know very much that, okay, so we can deduce that primitive irreducible means alpha is also a root of primitive irreducible polynomial with integer coefficient, and that's exactly the kernel will be generated by precisely that element. And this is exactly the proposition that we would like to say, that the kernel of map, let's say zx to c, and here of course fx goes to f of alpha, and here I am assuming alpha algebraic number is actually is generated by the primitive irreducible is generated by the primitive irreducible polynomial for alpha. And so the proof also, I think I can quickly sketch, and you can prove by yourself also, that now I think you can prove the proof itself by yourself, that anyway existence of this primitive irreducible polynomial is obvious from this one, that there exists an irreducible primitive polynomial for which fi of alpha is 0. And so we will take let's say f be the primitive irreducible polynomial for which f of alpha is 0. Then what we need to show, then aim is to show that kernel is precisely generated by this f, and that means we need to show that of course f will be contained, so ideal generated by f will be contained in the kernel, just because by the very definition of kernel this contains all polynomial with integer coefficient for which f of alpha is 0. So the ideal generated by this will be here. We need to prove the kernel is contained inside this principal ideal, and that you can also prove, because that means if you take G belongs to the kernel, yeah, what does this implies? That G of alpha is equal to 0, but f is primitive irreducible element, so this implies that f divides G. Yeah, means f divides G inside Q of x. Yeah, that we know. And again, if you use part A of a previous proposition in some lectures, that we have proven that if you have primitive polynomial and G is a polynomial with integer coefficients, And if the divisibility happens inside Q of X, this will imply that the divisibility happens inside Z of X. Yeah. And so therefore, what does this mean? That Z is multiple of F times H, where H belongs to Z of X. Yeah, and so therefore G lies inside the ideal generated by F, and so kernel. So this implies that kernel is precisely contained inside the ideal generated by. And so therefore it disproves the proposition. And so now I would like to stop the lecture and we will continue in the next lecture. So thank you very much.